Hello, everybody, and welcome to our latest Hubble Hangout. This is a place where you can come to learn about the latest news, science, and discoveries of the Hubble Space Telescope. My name is Tony Darnell, and I work at the Space Telescope Science Institute. And today we've got a really awesome hangout planned for you. When most people think of the Hubble Space Telescope and the science and observations it does, we often think of peering into the deepest corners of the universe and looking at some of the most distant galaxies we've ever seen. We've also looked at the amazing Hubble images of things within our own galaxy, of these, beautiful nebulae and star clusters and things like that. But Hubble also spends a lot of time looking closer to home, and by home I mean within our own solar system, and that's what we're going to talk about today. Some recent and some not so recent observations made by Hubble of the largest planet in our solar system, Jupiter. So, with me to discuss these latest Jupiter observations from Hubble is Dr. Amy Simon. She is the Senior Scientist for Planetary Atmospheres Research for the Solar System Exploration Division at NASA's Goddard Space Flight Center. She is also a co-investigator of the Cassini Composite Infrared Spectrometer and the Deputy Instrument Scientist for the OSIRIS-REx Visible and Near IR Spectrometer. Now, that has got to be the coolest name for an instrument I have ever heard, OSIRIS-REx. So, we've got to talk more about that at some point too, Amy. With me also is Dr. Glenn Orton. He's a planetary astronomer at the Jet Propulsion Laboratory in Pasadena. He's interested in IR astronomy, and I don't know of any astronomer around today who can't be interested in the infrared, planetary atmospheres, as well as extrasolar giant planets. And hopefully a little bit later on we'll have Dr. Mike Wong joining us. He's from UC Berkeley, who also works on planets, and he is a member of the Mars Science Laboratory. He's a collaborator for that, as well as he worked on the SAM instrument on board Curiosity. So we're hoping he can join us a little bit later to discuss some of this too. And of course, I want to welcome everybody. Welcome you guys to help me talk about these and to help me facilitate this discussion. With me today is also my colleague at Space Telescope Science Institute, Dr. Carol Christian, whose insights and perspective is always welcome here, and almost said Dr. Scott Lewis. Scott Lewis from Space Fan News and KnowTheCosmos.com. Welcome everybody, and let's go ahead and get started. I guess, Amy, let's start with you. Can you give us a general overview of what you're using the Hubble Space Telescope for in your studies of Jupiter?
Okay, well, I study the winds and the clouds on Jupiter, so I've been using Hubble now for 20 years, actually, it turns out, for a variety of different projects. And this particular project, we wanted to look at the Great Red Spot on Jupiter because we have a network of amateur astronomers, and they let us know that it looked like it was suddenly shrinking. Now, we've known it's been shrinking for a long time, but it looked like that rate had sped up. So they brought it to our attention, and we looked into it and basically requested the time with Hubble to look at that.
Okay, let's back up just a little bit, though, and let's get real
back
basic.
Up a little further? Let's let the audience know how they can get a hold of us too. So if they have any questions,
thank you, Scott. Remember that you guys can comment and ask us questions on the G Plus event page, the YouTube page that we're broadcasting on, as well as you can tweet to us using the hashtag Hubble Hangouts. Thanks, Scott. I almost forgot to do that. Well, I did forget to do that. So.
I mean, my ESP is tuned, but not for the entire internet right now. So.
That's right. So feel free to send us comments and questions. We're monitoring all kinds of different activities here, and we will hopefully have some time later in the Hangout, and we'll get to those questions. So, Amy, the Great Red Spot on Jupiter. Give us a little background on just give us the really basic background on what that is. For those of us who, maybe don't know very much about Jupiter, or they don't even know what we're talking about. What is this thing?
So the Great Red Spot is kind of Jupiter's trademark feature. It's a big storm in the atmosphere. It's pretty much been there since we've ever looked with modern telescopes. And it's kind of like a hurricane, but it's rotating in the opposite direction. So instead of being a low-pressure storm, it's a high-pressure storm. So it's a very strong, high-velocity wind storm that's been around for at least 150 years.
And do we know what is driving this storm? Or is there any indication what might be keeping it going for so long?
Actually, we don't know. Storms, cyclones, and anticyclones on Earth don't last anywhere near this long. High-pressure systems are more stable than low-pressure systems, And on Earth, of course, hurricanes break up when they hit land often, and we don't have land on Jupiter. But nonetheless, we have no reason why this storm should have lasted as long as it did. So that's one of the big mysteries, is what powers this storm and keeps it around for so long.
You say at least 150 years. Is there any indications that, what was the first observations we ever had of the Great Red Spot?
So that's where it gets a little tricky. We have definitive observations back to about 1870. It was well tracked from there forward, so we know exactly where it is and how big it's been since about 1870. But there are some very, very early papers by Galileo and Cassini in the 1600s where they talked about a permanent spot, but it kind of got mentioned once and never again. So we don't know in between if it's the same storm.
Yeah, and I guess I always wonder if Galileo could really differentiate between what he was looking at with the features on the disk versus maybe the moons around the planet too. So I don't know.
Exactly.
If there might have been a little confusion around that as well. So
yeah, the optics were not great.
Yeah, exactly. So
I think it's John Rogers in his book, who's trying to join us, who mentions that at some point, not very long after that, there's a painting of Jupiter hanging in the Vatican Museum with, of all things, looking like a great red spot sitting in it. So sort of undocumented evidence or someone's imagination about what should be there.
And what was this from? I didn't hear the first part of what you said.
Oh, this is from John Rogers' book. He's in a follow-on to a study about the morphology of clouds and their history in the atmosphere of Jupiter. It's called Jupiter, the Giant Planet, Cambridge University Press. John would join us, except he doesn't have Google and a microphone. So
yeah, I remember. That's right. We tried to get him in the Hangout, and he didn't have a computer with a laptop and a microphone.
Anyway, but this standing in for him occasionally. There's some evidence that there may be something like that in that region, but it's before the 150 years ago, and there's not very much conclusive.
Okay, so Amy, you say we've this thing has been shrinking. We know it's this feature has been getting smaller, but we've known this for quite some time, right? I mean, this is not new news. This is something we've known for a while. How long has this been? How long have we known that it's been getting smaller?
At least since the 1950s. There was another book by an astronomer named Peake in 1958, and he documented it in his book that he thought it was shrinking. But there was not a lot of high-quality observations. A lot of this was based on transit timings where people literally watched the time when the Great Red Spot hit the center of the planet and when it crossed over. So they used that to estimate how big it was. So the observations don't have a lot of fidelity, but they're actually quite good. And so from that time forward, we pretty much had some indication that it was shrinking. And the rate seemed somewhat constant. It varied a little bit now and again.
So it is getting smaller at a known rate then, or pretty much constant rate. You're saying?
Yeah. Over the long term, it's been a fairly constant rate.
So there's times where it gets smaller faster and slows down a little bit. So it does fluctuate somewhat.
Absolutely.
Okay, well, let's get to some of the...
Could I ask a question?
Yeah, go ahead.
So I wanted to ask Amy and Glenn a question. So we know that also, both through ground-based observations and Hubble, you all who do this research have seen other spots, though, right? Smaller spots. And could you talk a little bit about what we know about the duration of those and how big they are? And what their relationship might be, like where on Jupiter's face they are, and that's...
Okay, well, Jupiter often has a bad case of the measles. It has spots all over the place. But primarily we see them in the southern hemisphere. We don't know why. Most of them are pretty small in terms of the other round-looking ones, but some of them do last for quite some time. So there were a bunch of them, 3 of them, that formed in 1939. We actually saw them form. They condensed down to 3 white storms. They're all anticyclones, just like the Great Red Spot. And when they first formed, they were kind of big. They got a little bit smaller. Eventually, they got close enough to each other. They merged. And then in 2006, the one that was left turned red. And that's actually the one we call Red Spot Junior now. So it's smaller. It's a little bit farther to the south, but it's the same type of storm. And so far, that one hasn't gone away either. But that one's only about 80 years old.
So you mentioned the color. Yeah, and you mentioned the color. That's another interesting thing about the color. That it is red, but then you just said there were other storms that were white. So do we know why that is?
They began as white as well.
Yeah, we don't know. Most of them tend to be white. On rare occasion, we see one that turns red, like Red Spot Junior did. There's other small ones that form from time to time that are red. They tend to be deeper in the atmosphere, and they don't last very long. But we don't have a clue what the mechanism is that turns these red.
So Scott, let's turn to the Hubble observation. Scott's got the image up here on his screen now. These are observations of the red spot going back to 3 different periods. We had one in '95 with the WIFPIC 2 camera, and again in 2009 with WIFC 3, and again with WIFC 3 in 2014. Are these your observations, Amy? Were you making these with the Hubble?
Yes, they're all Hubble. I was actually involved in all 3 programs. They were all done for different reasons, but they nicely show how it's gotten quite a bit smaller since 1995.
It really has. I mean, you can see this really does a nice. And Scott also made an animated GIF earlier yesterday that that kind of shows the morphology of it as well. Oh, there it is. Okay, good.
Yeah.
So you can sort of see in this animation that it's getting a little bit smaller each time with each epoch.
Actually, this is in the animation, but I'll pull up here in a second. This is the still here from '95.
Oh, that's the first one. Okay.
And then here is 9 and 14. So we can see, and I'll pull up the animation here in a second, but frame by frame, I'm going, this is the most recent one. That's the previous one 5 years ago. So we can see a big difference there in the size.
Yeah, stop right there for a sec. What is that thing in the upper right or upper left there? What is that red spot there? Is that red junior? What is that?
No, that's not red junior. That's probably a cyclonic feature. Again, like I said, we get these other little spots that form from time to time, and they either get pulled apart or disappear on their own.
Okay.
So it's just another thing that's in the flow field near the Great Red Spot.
Right, and we tend to think of those as somewhat deeper in the atmosphere. So the darker stuff you see there is probably represents a clearing of clouds. It's kind of the opposite of the red spot in that sense. So you have to be really careful about differentiating between the visible color and the real tomography of the cloud system.
So here's Red Junior. I went and got a high-res image of it. So here's Red Junior. You can actually see the Great Red Spot over here.
Yeah.
And then here's Red Junior that we're looking at.
Right, and so those are observations we took shortly after it turned red.
Right. And to get a perspective of what we're looking at, here's Jupiter, and again in the southern hemisphere. See, there's a Great Red Spot, and there's Red Spot Junior.
Yeah. So I remember when I was first starting out in my career, Voyager had just passed Jupiter, and we got to see these time-lapse movies of the Jovian atmosphere, and we got to see the bands kind of going along back, sort of counter-rotating or going different directions and things like that. What are the bands like? What do those signify on Jupiter?
Well, you're exactly right. The winds are very strongly east-west on Jupiter. They don't change very much, so if you're at any particular location year to year, the wind speed doesn't vary very much at all. So we think, if we understand what's going on very well, they're almost like Hadley cells on Earth. So when the wind shears in one direction, you actually get uplift, and you should get more white clouds, and when it's going the other direction, you should get the clouds subsiding and clearing out, and that's where you see the darker color. Now, we also see little thunderstorms and other things that pop up in those darker regions. It's hard to see them in the white regions because that cloud is so high and thick. So that's what we think we're seeing is basically the equivalent of Jupiter's Hadley cells.
What's that? What are those?
So on the Earth, the Hadley cells are basically how you drive the circulation from the equator to the poles. And it creates, by going north and south, because we have a Coriolis force, you also get east and west out of it at the same time. So you end up getting the strong easterly and westerly wind jets on the Earth from some of this circulation.
So these are really strong winds in different bands, though, right? I mean, some of the bands in Jupiter are going in different directions too. I mean, that's
right.
Like the light and the dark bands are both going in different. Those are really strong. So you're saying that each one of those is one of those kinds of cells?
Yeah, the winds are on the very edges of the bands, and then that cell kind of defines the distance between the two wind jets. So you'll have an east wind jet and then a west wind jet, and they alternate all the way to the poles.
Scott, could you put another picture up? Just well, it doesn't matter which one. I wanna use it as a reference here for some of the bands on here because I wanna.
Yeah, let me pull one up here.
The other thing that I think is remarkable is in the different images that you were showing, and I'm sure every time you observe it, the different kinds of turbulence in the bands and around the spot. I mean, sometimes there's really strong whirls around it, and other times it kind of looks like there are waves around it, and yet it persists. It's pretty remarkable.
It's kind of true all over the planet. I mean, Jupiter's atmosphere is a fluid dynamicist dream. You've got nice straight flow, you've got turbulence, you have all sorts of things going on.
Right.
And fluid dynamics is so simple. When I put out a lot of these images, like, oh, I know what it is. It's global warming. I'm like, well, that's not really an answer, but it's such a complex system of fluid dynamics is not an easy thing at all. And seeing just how completely massive and how much larger in radius Jupiter is, plus everything else going on. Its chemical composition is different, the pressures and all the other things going on. It's just beautiful. And yeah, I could totally see, just if I was really into fluid dynamics, which I'm not, because that's really difficult, but if I was, this would just be a dream just to study this for the rest of my life.
It's interesting to note that region just northwest of the red spot, that looked like stripes of things, is a place where the jet stream is sort of heading toward the red spot and getting mixed up in an extremely turbulent area. You note on those Voyager videos and Cassini videos that that's kind of roiling, and that's one of the places where spectroscopically we see pristine ice, which we don't see on anywhere else on the planet. So that stuff is being moved up very fast. So those are the seats of very strong vertical winds as well, which we don't really otherwise have a good way of tracking.
So let's talk. So what are we talking about here? What are some of the characteristics of this red spot in terms of what exactly is going on there? I mean, are we looking at, what kind of, first of all, how high up is this in the atmosphere of Jupiter?
So the Great Red Spot itself, the clouds all are at different heights. So that's one thing you have to kind of get into your head, is that we think there's water clouds deep down. We think there's ammonia ice should be the white clouds we see high up, although as Glenn says, we don't see them spectroscopically very often. But we think the clouds kind of vary from about 1 bar of pressure, which is about the same as the pressure in the room you're sitting in now, all the way up to the stratosphere. So the Great Red Spot actually goes up all the way to the top of the troposphere. So similar on the Earth, the clouds kind of stop between the troposphere and the stratosphere. The highest ones on Jupiter hit about the same heights. But so we're talking, the equivalent of maybe 15 miles, though, above.
Oh, wow, that's amazing. So the the wind speeds here. I mean, how do we first of all, I guess I'd like to know how we measure these things. I mean, you look at things with Hubble and you see the images and you can take time lapses, you can get movies and stuff. But how do we know things like what the thing's made of, where, how high up it is, and things like that, and things like wind speeds? What are the best ways of measuring these characteristics?
Well, I think way back when, before we had really good observational data, a lot of it was from models. So we looked at what the temperature profile of Jupiter should be and said, well, these various compounds should condense out and make clouds. So you should get water clouds at a certain pressure, ammonia clouds at a different pressure. Now that we have much better imaging and spectroscopy, we can test those theories. And that's been one of our frustrations, is just what we said before, we should see ammonia ice all over the planet, and we don't. We should see other compounds all over the planet. We know they're there, but they're hard to see spectroscopically. And some of it is that Jupiter has haze over everything, and that kind of makes it hard to see certain things. But in terms of winds are things we can do really well with things like Hubble, because we can take time-lapse images and do exactly that. We look at the same spot and watch the clouds move, and we can measure them.
Did any of you guys, were you guys, I'm sure you guys were paying attention when the comet Hale-Bopp went into to Jupiter, right?
Shoemaker-Levy 9.
Shoemaker-Levy 9. Shoemaker-Levy 9. You guys were watching that pretty intently too. Were there any surprises there? Did you guys?
Everything was a surprise there.
I mean, as far as what you expected might happen to the planet itself.
I'll repeat what I
hear.
just.
Cries of pain, like, whoa.
We had We expected anything from massive changes like the ones we actually saw to absolutely nothing. And in fact, the answer is all of the above. All of the parts of the comet that were off the main line had nothing, apparently no mass associated with the rest. Made rather substantial changes both in the visual appearance that we saw with Hubble at the time and in the infrared, and quite far in the infrared, in fact.
So this, I remember when that. Did you see it, Scott? Did you see when it? Where'd you go? Are you there?
I'm here. Yeah,
Where
you can't get rid of me that easy. I'm actually looking for some time-lapse images of that the collision there.
Yeah, 1994.
Yeah.
Yeah. So I mean, let's talk. So the reason I bring that up is I wanted to talk a little bit about Jupiter's role in the solar system. And one of the things I always hear about Jupiter or Jovian, I always want to say jovial planets, Jovian type planets, is that they are actually a pretty important. Jupiter plays a pretty important role in our solar system, at least it has in the past, in terms of clearing out these comets and kind of protecting Earth a little bit. Is that right? Glenn,
yeah, that's true.
I think that is.
Mm-hmm.
Yes. We owe our existence in part because of Jupiter's position and mass in the solar system.
Yeah. So you are interested in exoplanets and other and Jupiter-sized planets around other star systems. How does Jupiter compare? What's Jupiter like compared to most of the other Jovian systems we know?
Yeah. I have to sort of start with a qualification that we can only talk about the things we happen to be able to see. So there's kind of selection effect, starting effect there. We don't see the really tiny things. I mean, we never see at this point in our technology Mercury around the sun. So we're talking about bigger things. We're sort of moving down to things that are the size of the Earth slowly, particularly Kepler. The Kepler mission. But as it stands now, the statistics favor most of the planets that we know in the known space are Neptune size. And Jupiter is kind of an anomaly. And our solar system, in the way it's made up, is kind of anomalous too. Many of these large-sized planets are quite close into the sun, where, say, Earth or Mars are even closer compared with our sun. But again, I worry that that's a bit of a selection effect, because those are the things we see most easily. So we're kind of, Jupiter's a big, the 800-pound gorilla in our solar system, and maybe many, many others as well.
Yeah, I remember that. I remember hearing that when one of the Kepler news releases, it was advertised that they, that they were a little bit surprised at how many Neptune-sized planets there were out there. That and did say that they were very close to their star like this. So so let's get back to the red spot for just a little bit. It's shrinking. We've known it's been shrinking for a while. Is it going to disappear? Do we have a rate at which it will no longer be there? What's going to happen? Anybody, any guesses? Any projections?
Well, we had looked at this actually earlier in. I had a paper in 2002 where we were looking at spacecraft data in particular, Voyager, Galileo, Hubble, looking at the rate of shrinkage. And at that point, we were estimating it would be round by about 2030. At the current rate, it's sped up. So if it sustains this rate of shrinkage, it'll be round even faster. In terms of what does that mean, is it going to go away? Well, part of the problem is we don't understand what's sustaining it in the first place. And so one of the things we hope to do with this data is actually look at not just the Great Red Spot, but everything around it, and see what else is changing, so that we can determine if there's anything that feeds the Great Red Spot that is slightly turned off now, or if there's some other thing that counters it. And so that's kind of the stuff we want to use this data in particular to look for.
So you brought up, that's an interesting point. We don't really know what's driving it, so it's hard to say how long it might sustain itself. Now, we've sent probes into Jupiter. I mean, a probe, I should say. I was hoping Mike would be here by now and we could talk a little bit more about this. But maybe you guys, maybe Glenn, you can comment on this a little bit too. The Jupiter probe back that was a part of the Galileo mission was sent in to measure the atmospheres, the atmosphere of Jupiter. Did it shed any light on this problem?
Not particularly. The probe itself went into a part of the planet that we wish were a bit more commonplace. It went into an extremely strange area, which has one of the least cloudy parts of the planet completely, cloudless and dry. The Galileo probe, which went in December 7, 1995, just looked at one point, and we realized, we had supporting ground-based work at the time that showed that it was coming into a region that was quite strange, and so we really are careful to take, not to extrapolate some of those data to the whole planet in general, and in fact, because of the lack of water and in part lack of clouds that we see in there, we created the Juno mission, which is going to be using microwave to sense as deep as 100 bars of pressure to look for water and ammonia in various lots of the planet. For mapping, Amy might remember more about the mapping, what Galileo, the orbiter did, the orbiter instruments did for the Great Red Spot. We had about 3 orbits in which we sort of targeted the red spot in some ways. And I don't know if you want to say any more about that.
Yeah, go ahead. Scott's got a graphic up of a fully deployed antenna on Galileo. But,
yeah, we kind of wish.
Actually, just make that sting.
Right.
Yeah.
It's like right here. This is what should have happened, but
Right.
If we could go back, yeah.
No, I was an interdisciplinary scientist on Galileo, and remember the photopolarimeter radiometer experiment. So we got.
I don't hold punches here, so you're welcome.
Yeah.
Yeah, so Glenn's right, though. If you look at the region just north of the equator, there's kind of grayish, bluish areas, and those are the areas with essentially no cloud, and that's exactly where it went in. We actually had Hubble data at the same time, too. We could show you exactly which hotspot or which opening it went in. We call them hotspots because they glow in the infrared because the heat can come out without the clouds in the way. But we did map the Great Red Spot with Galileo, and we were able to do some of these properties about cloud height and also measure the wind velocities at that time. And again, it's a very fierce storm. We're talking 500 miles per hour winds. So.
Okay, well, we're getting quite a few questions on the Q&A app, and before too many of them scroll by, I'm going to go ahead and let me get one. Here's one from Michael Jobin, who asks. Let me just select it here. Have others documented this finding before the HST stuff? Because I have seen the change over the years. So I guess he wants to know, are there other telescopes besides Hubble recording this shrinking or this change in the red spot?
Sure, it's been primarily ground-based data. As I was saying, John Rogers has it in his book, and Peake also has it in his book, so 1950s and then 1995. So just from ground-based telescopes, backyard telescopes, we've been able to document the shrinking.
Yeah, it's the anomalous shrinking, the accelerated shrinking that actually it's an amateur observation that got us interested in to start with. So we rely to a large extent sometimes on the amateur community for information about what's going on.
Yes, we welcome citizen science.
Yeah, this is a good area where people can really contribute well, I would imagine. So Tony Michael is asking, to give perspective on how big Jupiter is, how many Earths could fit inside?
Inside all of Jupiter or the Great Red Spot?
Jupiter.
Let's do red spot.
Back when Voyager flew by and the Great Red Spot was bigger, we used to say 3 Earths, and it's now more like 1.5.
It's quite substantially smaller.
Mm-hmm.
Okay, and here's from Hans Milling is asking, is the red spot always facing Earth?
No, Jupiter rotates very quickly, about 10 hours, so we have to time it so the Great Red Spot's on the right side when we look, but the red spot also moves. It's not a fixed feature like a mountain, so we have to track very carefully when we want to target with something like Hubble.
Yeah, I wish there's some really nice animations you can get online where you could see the motions of the planet in its entirety, both from Voyager as well as other animations and other observations that are really amazing to look at. So you can definitely do a search on those and find out.
It's something we run into on the Virtual Star Party, one of my other shows. We're always trying to be able to see it, and it's never we're never able to see it when we're observing live. We always get it maybe a half hour afterwards, something like that, because it rotates so quickly, and it's a moving target.
But it is a fun planet to look at, that's for sure,
It's
in a ground-based amateur telescope.
Yeah. Well, it looks like Mike Wong has joined us. Hi, Mike. Welcome.
Hi. Thanks.
Hi. Mike is, as I started to say before, he's a research scientist at University of California at Berkeley. He works on the SAM instrument on board Curiosity, and you apparently are interested in the Great Red Spot as well, correct? Right, Mike?
Yeah, I'm really a Jupiter guy, but I
Where the money.
I started out working with the Galileo probe mass spectrometer, which took measurements as it descended into Jupiter's atmosphere, and the same team built this mass spectrometer that's on Mars. So I'm working with them now.
Okay. Well, I've always wanted to do a curiosity hangout, so I'm going to have to bother you again at some point and get you on a Mars and curiosity hangout. We talked about that a little bit.
Okay.
But so yeah, we just got through talking about some of the things that was learned when the probe went into Jupiter's atmosphere, and Glenn was telling us that we sent it into a pretty quiet part of Jupiter. Hubble was watching when that happened. It didn't really give us any insights, nor was it designed to, I don't think, to give us any insights into the Great Red Spot itself. But I thought I would ask, now that you're here and you worked on the mission, what were there any things that stood out to you with the Jupiter or with the Galileo probe mission?
Well, actually, one of the main goals was to figure out how much water is on Jupiter, and did you guys talk about how that didn't work out so well?
Right. and why it's kind of the basis for the Juno mission now. So
yeah, so we'll get it a different way. But actually, some of the research we're doing uses vortices like the Great Red Spot and Oval BA to figure out how much water is on Jupiter, because when water clouds form, this creates, some of us think this creates a stable layer, and by figuring out how stable that layer is, kind of like an inversion that we talked about in the Earth's atmosphere, we can use these vortices to figure out how stable that air is, and that gives you a clue about how much.
Oh, are you there, Mike?
Yeah. Did you lose me?
Yeah, I lost you where you said it gives us a clue about, and presumably it was about how much water vapor is there.
Yeah.
Yeah. Okay. All right. Yeah. So yeah, your connection's a little bit jittery, but
sorry about that.
You should be back now. Okay. So,
but actually, Hubble did not observe right when the probe went in.
right. It was a little bit
they
before.
were just near. Okay, I'm sorry, I misunderstood what Amy said. Then I thought.
No, it observed the spot it went into, the opening it went into, but not at the same time.
Oh,
Yeah.
okay.
Yeah.
All right.
Jupiter was really close to the sun, as seen in the sky. And Glenn actually did some really fancy tricks to observe it from the ground.
Yeah, we covered the entire NASA Infrared Telescope facility with the largest filter I've ever seen, which is 3 meters in size, and it emitted radiation at and greater than 5 microns and cut out everything else in the visible, sort of like putting a potato chip bag over the telescope. And so we had did that and discovered there was a 5 micron hotspot right where the probe was supposed to go in, and everything that we got from the probe coincided with the idea that this was in fact the kind of dry and cloudless area we expected from that kind of region. And that was kind of strange. It's also a kudo on the need and importance of ground-based observations of planets when missions go by and don't have all the resources they would really like when they're going on.
Okay, I want to get to another question real quick that I don't think we answered this specifically, but Hans Milling is asking, are the wind speeds the same around the Great Red Spot, presumably, even though the red spot is shrinking? I don't think we answered that specifically.
So hey, Hans. Actually, we're still looking into that. We just got the data, and this is the main reason, one of the main reasons why we went to Hubble to do this. So we don't want to spill those beans quite yet.
Because we're not done.
Stay tuned. Stay tuned. Yeah. Presumably you're working on your paper now, right?
Well,
right.
Paper calculations.
Okay, so let's go. Let's see. Are there? Oh, it just scrolled past. how long has the red spot been on Jupiter, and how long do you suppose it will last? Estimated time, of course. That's from Tony Michael, and I think we touched on this already a little bit. Amy said that we have observations of it going back at least 150 years, and as far as the estimated time remaining, as Amy also said, we don't know what's driving it yet, so it's hard to answer that question. We need to understand more of the dynamics of the red spot, and this just highlights something that I find, it's also true in solar physics. It's amazing what we're still learning about the things very close to us. Like, there's a lot about the sun we don't know. There's a lot about the planets we're still learning, and so a lot of this stuff is coming out with observations like the Hubble, but unfortunately the answers to those questions there's nothing definite there yet. Do you guys want to add anything to that?
Yeah, I actually want to add to that question because
Okay.
Amy and Glenn, so I thought that the Great Red Spot may have been seen by Cassini in the 1600s. What are the issues about whether that's the same spot or not?
Yeah, we mentioned that briefly. Part of it is, of course, we know the optics weren't that great. The original papers, which I did go back and look up, which were challenging to read, to say the least, it's not clear if it's the same latitude. It might have even been the northern hemisphere, not the southern. And some of the descriptions don't seem to quite match up. And the fact that we know that it's shrinking, it would have been quite big back then. So it may not be the same storm. And as Glenn also said earlier, there's a picture that was found in the Vatican that showed Jupiter with a spot on it, but it's kind of anecdotal evidence at this point. We don't have enough to say for a fact that it's the same thing, but it might be.
Well, I'm going in my TARDIS later this afternoon, and I will take some pictures for you guys and beam them back, and we will know for sure.
Okay, get back to us on that.
I mean, if you see pictures in John's book, or any of the pictures you might get elsewhere on that show Jupiter in the 1880s, 1890s, that show the red spot, you'd swear it's the Great Red Sausage. This is 30 degrees of longitude. This thing is big. And this is dropping down since then. But I think the idea of Great Red Sausage as a name is never caught on. But
Great Red Sausage, yeah, that's got... Okay, let me move on.
Calm down, Tony. Calm down.
Jan Kellner is asking, does Jupiter have a solid core? And if so, how big is it and what's it made of? Anybody?
That's a great question. I love that question.
Yeah. There's probably some heavy material, metal, silicon, heavy things that form a core as they do in the cores of all the giant planets. That's because we presume that there's a mixture of solar-like elements everywhere. They were added to afterward, and that's kind of the mysteries of how things formed. There are theories, and there's no direct evidence, but there are theories on how much there is in each of these planets. And that's about it. It's not very big for Jupiter or Saturn. And we measure in terms of several Earths in terms of mass, as I recall. I'm quite happy to be corrected on any of that in your mind.
No, that's about what I would say too. The best guess at the moment is 2 to 3 Earth masses of heavy elements.
Yeah.
Okay. Now here's a loaded question. And this comes from Chris Marshall. Are there any experiments that could provide more information on what's powering the Great Red Spot if money wasn't a limiter?
Oh.
If money were no object, guys.
And send a lot of probes into Jupiter.
Awesome.
I mean, it would. It seems sort of ironic. It's all due to money that we send many probes into the atmosphere of Venus, which has, in some ways, is one of the most homogeneous we know about. And we send one probe into Jupiter, which is probably the most inhomogeneous one that we see, at least visually. But that's life. Jupiter's pretty far away, and Venus is a lot closer.
Yeah, there's a lot of challenges, I would imagine, in getting into Jupiter.
And you want to look at wind speeds all around the red spot. You want to send something into the red spot.
Yeah, probes, well, maybe you could send balloons that could get wind speeds. Probes would give you maybe composition, cloud densities at that location. Another great thing would be a weather satellite around Jupiter.
Mm-hmm.
Right.
Something that's because we've sent spacecraft there. They can't take images all the time, and so we get bits and pieces here and there. But a dedicated weather satellite around Jupiter, or hey, even around the Earth, but with a powerful telescope, could get that job done.
Yeah, Mike and I would both like a dedicated Hubble of our own.
Yeah.
Oh, I want one of those too, actually. Yes.
Right.
I like my own Hubble Space Telescope too.
I'll get on that grant as well. Let's just, I'm sure if they mass produce them, it'll be cheaper, right? So let's just get a bunch of them out
That's
there.
right. There's cost savings in doing it more than once. That's right. That's exactly right.
Yes.
Okay, so here is one that's getting a lot of pluses here from Craig Landon. Are there any known similarities atmospherically between the Great Red Spot and the hexagon at the poles of Saturn? Similar composition, different location due to weather factors?
Well, on Saturn, the hexagon is part of a whole polar vortex. Polar flows are a little more complicated. So it is still a vortex, a storm that rotates in that same sense, but the polar regions are a little special. They can actually make hexagons in a lab with rotating fluids, and it just has to do with how winds move around, flow moves around a pole. In the case of the Great Red Spot, it's not the pole. So.
Okay. Yeah, I'm glad you sort of explained what that was, because I was going to ask you to tell us what the hexagon is. So it's a polar flow, whereas the red spot is something much further down on the latitude scale.
Yeah, and it is similar to the what we call the polar hexagon. Those who were experiencing pretty cold winters in the U.S. this past winter. The polar hexagon is, it's also a wind belt that's encircling a vortex, and it has waves on it. And so in the case of Jupiter and Saturn, those waves can become stable enough so that they look like the sides of a hexagon. And also in labs, you can get a pentagon or a septagon, other shapes as well.
Oh, okay. Let's see. And here's one from, that's a good question, Craig. Thank you.
Could I ask a question?
Of course, Carol.
No, Carol.
No, post it on the website.
Let it go.
Okay, Scott, I will speak to you later.
Right.
So we also know that Jupiter has very strong magnetic fields, and that the magnetic fields interact with its moon system and the surrounding area. Does the magnetic field have anything to do with or influence the red spot that you know of, or any of these spots?
Well, the magnetic fields, of course, drive auroras on Earth, and on the other planets we do see aurora on Jupiter. And we can actually see the magnetic footprint of Io in the atmosphere as well. So basically, wherever the magnetic field intersects a planet, or a moon rather, it can actually bring a footprint down onto to Jupiter itself, but it tends to be very high up in the atmosphere that you see it. You see very localized heating and so on, but it's extremely high up in the atmosphere. Glenn, I don't know if you want to add to that.
You know, if we look at wavelengths like 90 nanometers, where we have a lot of methane absorption with wide field camera 3, or further in the infrared from the ground, we are susceptible to seeing particles very high in the atmosphere because there's methane and hydrogen gas that are absorbing all of the photons before they get reflected back to us. When we look at the planet there, we see one of the highest things in it. The brightest parts is the Great Red Spot, or Red Spot Junior. But other than that, the poles are actually one of the most striking parts of the planet, because we presume that particles are being created by this interaction of chemistry driven by energetic particles flowing down the magnetic field into this auroral oval. And auroras, the magnetic field of Jupiter is displaced compared with the rotation axis, so they tend to be streaming out onto the edges of the polar vortex itself. Some of them get entrained, that is, corralled into that polar vortex, and some spread outward. More of them get, pardon the phrase, sequestered inside the southern polar vortex, and in the north, some of them spill out. So we have these two very well-defined vortices, including Jupiter's. Sometimes has not quite as stable as a hexagon in Saturn, but Jupiter's polar vortex has boundaries and waves that tend to move a bit more, maybe 5-sided or 6-sided, depending when you look. um, at this polar, what the amateurs would call a polar hood. But there's some stuff spreading out because the polar vortex, pardon me, the auroral oval actually oversteps that boundary and starts spreading things out, and that diffuse further south of the planet. But direct influences on the red spot itself, not so much, as in none that I know of.
Okay, let's just take one more question here that we've already talked about this just a little bit, but we'll address it directly from Jeff Kesner, who's going about the any interesting information that came out of the study of clouds generated when Comet Shoemaker 9 Levy 9 impacted. I believe we talked about, Glenn had said that was basically an amazing event in all respects. But Mike, you weren't here when we talked about that. Do you have anything to add about that impact? Did you learn anything new from that? Hello?
Yeah.
I can't hear you.
Muted.
Okay, he's breaking
Okay,
up.
can you hear me now?
Yeah, I can hear you now.
No.
Yeah. Yeah.
Okay, sorry. Well, I'm sure you guys covered most of the stuff. I would say, like, mainly that this may have been an asteroid that hit the planet instead of a comet.
In 2009, you mean? In 2009, you mean?
Yeah, was that the question, or are we talking about Shoemaker
About
Levy 9?
Shoemaker 9. Did we learn anything more about what was it you thought you learned about the planet for the Shoemaker Levy impact?
Well, actually, at that time, I was a radio astronomer, and so I was in Green Bay, West Virginia. Yeah, no, a lot of exciting stuff happened. The comet brought a bunch of dust into the system, and you just talked about auroras. Well, auroras are caused when these charged particles in the magnetosphere smash into the atmosphere at really high velocities. So you introduce a bunch of dust into the system, and that can soak up some of these electrons. And we saw massive changes in the radiation environment around Jupiter. So that was pretty cool, and it gave me a one-week trip into the remote mountains of West Virginia where I mountain bike.
Oh, that's awesome. Okay.
It did also deliver stuff into the upper atmosphere, and for the first time it sort of created markers that we could use as we watch the flow north-south, which we don't usually get to see because it's so slow. You can see things start to circulate. So our first indications about the circulation of meridianal north-south circulation of the planet starting got a little bit of actually observational constraints.
And that was from carbon monoxide, is that right?
Oh,
I mean, that was the one that
carbon dioxide also, there are just particulates as well.
Particulates, right.
All right, so what's coming up? Or do you guys, I mean, I know you guys are working on your paper now based on the observations that were taken. Any plans, any future observations with Hubble planned, or is this pretty much it for now?
Oh, we're going to try.
We're at the mercy of the science community right now. We've submitted proposals to look up some more, of course. So we'll just see if they get time.
Right.
So you have proposed for more Hubble time then?
Yes.
Yes, we have.
Oh yeah.
And we have to proposed for archive time as well to start looking a bit more carefully at the past on the Great Red Spot in particular. And I think jump off from that, we will be looking at Hubble, probably applying for Hubble data to be supporting the Juno mission when that arrives as well.
And what's the timeline for that? Tell us a little bit about that.
Mid-2016 to late 2017. A lot of the designated remote sensing orbits are going to be fairly early in the mission. Unfortunately, when Jupiter's not very far from the sun, so they're in the exclusion zone, for the solar exclusion zone. But we'll be looking for time. Juno will be looking in some very narrow swaths of longitude. It's a polar orbiter, and it's spin stabilized. So it's going to be looking at think of a narrow strip in longitude that goes a bit wider toward the pole. So we want to use Hubble and other telescopes to provide a lot of context to that as well. Juno has one camera, and it simply is a methane filter and wideband red, green, blue. It's largely education, public outreach camera. We use it for scientific purposes, but it's not considered space-grade instrument. So so as I heard, Wide Field Camera 3 is. So we will be working that out.
Okay. All right. Great. Well, good luck on the proposal. I hope to get more Jupiter observations from Hubble. Are these all the three epochs that we talked about already? Is that been the three main times, Carol, that Hubble has looked at Jupiter? Do you know of any others?
There's a lot.
No, there's quite a few.
Yeah, there are, and that's why to Glenn's point is that it does help to look at the archival observations. And I'm speaking for our guests, but I would guess that not only looking at the red spot, but looking at the rest of Jupiter, even when it doesn't have the red spot in the field of view, could be very informative about the bands and the circulation patterns, because you have to look at that as well. So we've actually looked at Jupiter quite a lot. I mean, we looked at a lot of solar systems objects quite a lot with Hubble.
Mm-hmm.
Yeah. And it always changes in some often very surprising ways.
Yeah.
And pretty much every imaging instrument on Hubble has collected data on the Great Red Spot. So ideally, we would like to compare data from all these different instruments so we can cover as much of its history as we can at high resolution.
Yeah. One of the things that interests me as much as the dynamics and the north-south, east-west flow is the color, which is as involved both Amy and Mike as well. And it's interesting that we see the red spot that's very deep color most often when the rest of the material around it is light in color, which is kind of anomalous. And that this is one of those, which was saying during Pioneer, the early 1970s. You look at Pioneer images and you see the very white South Equatorial belt, which is normally dark, and the red spot is very deep red. Toward Voyager, the red spot's not quite so red, and the material around it is dark, which it kind of usually is. Right now it's really interesting because the material around it is dark, and the red spot is really, really red, which is a little bit different from any other time we've looked at it. So we're in an intriguing epoch right now.
Yeah, it sounds like a lot is going on with respect to Jupiter right now. So,
Yeah.
Okay, well, I guess we're about out of time now. I want to thank everybody for participating in this hangout. This was really interesting. I really got a lot out of it. We'll look for your paper. Hopefully we'll be able to talk about a few more things we didn't bring up here at this particular time. But there you have it, folks. The Great Red Spot. It's shrinking. It's getting rounder. It's changing as we speak, and Hubble has been looking at it, and these all of these really very smart people have been looking at Jupiter and telling us what they're finding out. So I hope you enjoyed this hangout. I want to thank you, Amy, Glenn, and Mike, for joining us. Thank you all very much. And Carol, Scott, it's been a lot of fun. We're going to be back for a quick programming note. Carol and Scott and I will be doing these hangouts on a more regular basis starting in June. Our next hangout is June 12th. We're going to be giving you guys a Frontier Fields update on the Frontier Fields program. So I hope you guys can make it there. And the time will be 3 p.m. Eastern instead of 4 p.m. Eastern, which makes that 7 o'clock Greenwich Mean Time. And so we hope you guys can make it, and we will see you next time. I want to thank you all for watching, and keep looking up.
Thanks, sir.
You're using the Hubble Space Telescope for in your studies of Jupiter.
Okay, well, I study the winds and the clouds on Jupiter, so I've been using Hubble now for 20 years, actually, it turns out, for a variety of different projects. And this particular project, we wanted to look at the Great Red Spot on Jupiter because we have a network of amateur astronomers, and they let us know that it looked like it was suddenly shrinking. Now, we've known it's been shrinking for a long time, but it looked like that rate had sped up. So they brought it to our attention, and we looked into it and basically requested the time with Hubble to look at that.
Okay, let's back up just a little bit, though, and let's get real
back
basic.
up a little further? Let's let the audience know how they can get a hold of us, too, so if they have any questions.
Thank you, Scott. Remember that you guys can comment and ask us questions on the G+ event page, the YouTube page that we're broadcasting on, as well as you can tweet to us using the hashtag Hubble Hangouts. Thanks, Scott. I almost forgot to do that. Well, I did forget. that.
I mean, my ESP is tuned, but not for the entire internet right now. So
That's right. So feel free to send us comments and questions. We're monitoring all kinds of different activities here, and we will hopefully have some time later in the Hangout, and we'll get to those questions. So, Amy, the Great Red Spot on Jupiter. Give us a little background on just what. Give us the really basic background on what that is for those of us who maybe not know.
70. But there's some very, very early papers by Galileo and Cassini in the 1600s where they talked about a permanent spot, but it kind of got mentioned once and never again. So we don't know in between if it's the same storm.
Yeah, and I guess I always wonder if Galileo could really differentiate between what he was looking at with the features on the disk versus maybe the moons around the planet too. So I don't know.
Exactly.
If there might have been a little confusion around that as well. So
yeah, the optics were not great.
Yeah, exactly. So
I think it's John Rogers in his book, who's trying to join us, who mentions that at some point, not very long after that, there's a painting of Jupiter hanging in the Vatican Museum with, of all things, looking like a great red spot sitting in it. So sort of undocumented evidence or someone's imagination about what should be there.
And what was this from? I didn't hear the first part of what you said.
Oh, this is from John Rogers' book. He's in follow-on to a study about the morphology of clouds and their history in the atmosphere of Jupiter. It's called Jupiter, the Giant Planet, Cambridge University Press. John would join us, except he doesn't have Google and a microphone. So
yeah, I remember. That's right. We tried to get him in the Hangout, and he didn't have a computer with a laptop, and they don't know very much about Jupiter, or they don't even know what we're talking about. What is this thing?
So the Great Red Spot is kind of Jupiter's trademark feature. It's a big storm in the atmosphere. It's pretty much been there since we've ever looked with modern telescopes, and it's kind of like a hurricane, but it's rotating in the opposite direction. So instead of being a low-pressure storm, it's a high-pressure storm. So it's a very strong, high-velocity wind storm that's been around for at least 150 years.
And do we know what is driving this storm? Or is there any indication what might be keeping it going for so long?
Actually, we don't know. Storms, cyclones, and anticyclones on Earth don't last anywhere near this long. High-pressure systems are more stable than low-pressure systems. And on Earth, of course, hurricanes break up when they hit land often, and we don't have land on Jupiter. But nonetheless, we have no reason why this storm should have lasted as long as it did. So that's one of the big mysteries, is what powers this storm and keeps it around for so long.
You say at least 150 years. Is there any indication that, what was the first observations we ever had of the Great Red Spot?
So that's where it gets a little tricky. We have definitive observations back to about 1870. It was well tracked from there forward, so we know exactly where it is and how big it's been since about 1870.
Correct. So we got to talk more about that at some point too, Amy. With me also is Dr. Glenn Orton. He's a planetary astronomer at the Jet Propulsion Laboratory in Pasadena. He's interested in IR astronomy, and I don't know of any astronomer around today who can't be interested in the infrared, planetary atmospheres, as well as extrasolar giant planets. And hopefully a little bit later on we'll have Dr. Mike Wong joining us. He's from UC Berkeley, who also works on planets, and he is a member of the Mars Science Laboratory. He's a collaborator for that, as well as he worked on the SAM instrument on board Curiosity. So we're hoping he can join us a little bit later to discuss some of this too. And of course, I want to welcome everybody. Welcome you guys to help me talk about these and to help me facilitate this discussion. With me today is also my colleague at Space Telescope Science Institute, Dr. Carol Christian, whose insights and perspective is always welcome here, and almost said Dr. Scott Lewis. Scott Lewis from Space Fan News and KnowTheCosmos.com. Welcome everybody, and let's go ahead and get started. I guess, Amy, let's start with you. Can you give us a general overview of what... Hello, everybody, and welcome to our latest Hubble Hangout. This is a place where you can come to learn about the latest news, science, and discoveries of the Hubble Space Telescope. My name is Tony Darnell, and I work at the Space Telescope Science Institute, and today we've got a really awesome hangout planned for you. When most people think of the Hubble Space Telescope and the science and observations it does, we often think of peering into the deepest corners of the universe and looking at some of the most distant galaxies we've ever seen. We've also looked at the amazing Hubble images of things within our own galaxy, well, these beautiful nebulae and star clusters and things like that. But Hubble also spends a lot of time looking closer to home, and by home I mean within our own solar system, and that's what we're going to talk about today. Some recent and some not so recent observations made by Hubble of the largest planet in our solar system, Jupiter. So, with me to discuss these latest Jupiter observations from Hubble is Dr. Amy Simon. She is the Senior Scientist for Planetary Atmospheres Research for the Solar System Exploration Division at NASA's Goddard Space Flight Center. She is also a co-investigator of the Cassini Composite Infrared Spectrometer and the Deputy Instrument Scientist for the OSIRIS-REx Visible and Near IR Spectrometer. Now, that has got to be the coolest name for an instrument I have ever heard, OSIRIS.